In this lecture, we're going to talk about querying data frames. The first step in the process is to understand Boolean masking. Boolean masking is at the heart of fast and efficient querying in both NumPy and in Pandas, and it's analogous a bit to bit masking, which is used in other areas of computer science. By the end of this lecture, you'll understand how Boolean masking works and how to apply this to a data frame to get out the data that you're interested in. Now, a Boolean mask is an array, which can be thought of as a one dimension, like a series, or two dimensions, like a data frame, where each of the values of the array are either true or false. This array is essentially overlaid on top of the other data structure that we're querying. And any cell aligned with the true value will be admitted into our final result, and any cell aligned with the false value will not. Let's take a look. So let's start with an example and import our graduate admissions data set. So first we'll bring in Pandas. So import Pandas as PD. Then we'll load in our CSV data file. So we'll make a new variable df is equal to pd.readCSV. And remember, we're going to use our index column 0. And then we're going to clean this up and fix a couple of the poorly named columns like we did in the previous lecture. And so I'm going to use our list comprehension here. X.lower.strip for x in df.column. So this is just iterating over a bunch of strings and turning them lowercase and stripping out a white space from either side. And let's take a look at the results. So Boolean masks are created by applying operators directly to the Pandas series or data frame objects. For instance, in our graduate admission data set, we might be interested in seeing only those students that have a chance higher than 0.7 of being admitted. To build a Boolean mask for this query, we want to project the chance of admit column using the indexing operator and apply the greater than operator with a comparison value of 0.7. This is essentially broadcasting a comparison operator, greater than, with the results being returned as a Boolean series. The resultant series is indexed where the value of each cell is either true or false, depending on whether a student has a chance of admission higher than 0.7. So we'll create this thing called an admit mask, and we'll say df sub chance of admit, and then we're going to broadcast against this column. So remember, we're just projecting a single column, the greater than operator, and pass it a value of 0.7. And let's take a look at what that admit mask is. So this is pretty fundamental, so take a moment to look at this. The result of broadcasting a comparison operator is a Boolean mask, true or false values, depending on the results of the comparison. Underneath, Pandas is applying the comparison operator that you specified through vectorization, so it's efficiently and in parallel, to all of the values in the array that you specified, which in this case is the chance of admit column of the data frame. The result is a series object, since only one column is being operated on, filled with either true or false values, which is what the comparison operator returns. So what do you do with the Boolean mask once you've formed it? Well, you could just lay it on top of the data to hide the data that you don't want, which is represented by all the false values. We do this by using the .where function on the original data frame. So df.where, and we just pass in a single parameter, the admit mask. And let's take a look at what that data frame looks like, and we'll add the .head. So we see that the resulting data frame keeps the original indexed values, and only data which met the condition was retained. All of the rows which did not meet the condition have NaN data instead. But these rows weren't dropped from our data set. They're still there, they're just not in numbers. The next step is, of course, if we don't want the NaN data, that we use dropna function, and this is quite common. So we actually do df.where, pass in the admit mask, and then on that resultant data frame called .dropna, and then on that called .head. So the returned data frame now has all of the NaN rows dropped. Notice that the index now includes 1 through 4 and 6, but not 5. Despite being really handy, where isn't actually used that often. Instead, the Panda devs created a shorthand syntax which combines where and dropna, doing both at once. And in typical fashion, they just overloaded the indexing operator to do this. So here's an example. So we do df, and then inside of the indexing operator, we actually put our computation for the Boolean masks. So df sub chance of admit greater than 0.7 head. So I personally find this much harder to read, but it's super common when you're reading other people's code. So it's important to be able to understand it and to write it. Just reviewing this indexing operator on the data frame, it now does three things. So first, it can be called with the string parameter to project a single column. So if we do df sub GRE score dot head, we get a single column. Or you can send it a list of columns as strings. So df sub GRE score and TOEFL score as a subparameter list. Or now you can send it a Boolean mask. So df, and then we put in here, let's say df sub GRE score is greater than 320, and look at the head of that. And each of these is mimicking functionality from either .lock or .where.dropna. Before we leave this, let's talk about combining multiple Boolean masks, such as multiple criteria for including. In bit masking and other places in computer science, this is done with AND. If both masks must be true for a true value and to be in the final mask, or if only one needs to be true. Unfortunately, it doesn't feel quite as natural in Pandas. For instance, if you want to take two Boolean series and AND them together. So here we do df sub chance of admit greater than 0.7, and let's say we want df sub chance of admit less than 0.9, so maybe these are the people who got close to getting admissions and we want to encourage them to apply again. But that didn't work. And despite using Pandas for a while, I actually find I regularly try and do what I just did. The problem is that you have a series object, and that Python underneath doesn't know how to compare two series using AND or. Instead, the Pandas authors have overwritten the pipe and ampersand operators to handle this for us. So we actually have to write df sub chance of admit, and then we use the ampersand sign to AND these together. And so here we can see this is the combination, the bitwise AND of our two Boolean masks. So one other thing to watch out for is the order of operations, and this gets me regularly as well. A common error for new Pandas users is to try and do Boolean comparisons using the ampersand operator, but not putting parentheses around the individual terms you are interested in. So we could just write what we wrote before, but this time without parentheses. So df sub chance of admit greater than 0.7, ampersand df chance of admit less than 0.9. And we see that there's an error for this as well. The problem is that Python is trying to bitwise AND a 0.7 and a Pandas data frame when you really want to bitwise and broadcast data frames together. Another way to do this is actually just to get rid of the comparison operator completely, and instead to use the built-in functions which mimic this approach. So we could say df sub chance of admit dot gt for greater than 0.7, and then bitwise AND this with the df chance of admit dot lt of 0.9. So these functions are built right into the series and data frame objects, so you can actually chain them too, which results in the same answer and the use of no visual operators. You can decide what looks best for you. So df sub chance of admit dot gt 0.7 actually returns our item, and then we can say dot lt 0.9 right on that, and so we can chain these together. So this only works if your operator, such as the less than or greater than, is built into the data frame. But I certainly find the last code example to be much more readable than the one with the ampersands and the parentheses, so you might want to consider using this. You need to be able to read and write all of these and understand the implications of the route you're choosing. It's worth really going back and re-watching this lecture to make sure that you have it. I would say 50% or more of the work you'll be doing in data cleaning involves querying data frames. In this lecture, we've learned to query data frames using Boolean masking, which is extremely important and often used in the world of data science. With Boolean masking, we can select data based on the criteria we define, and frankly, you're going to use this everywhere. We've also seen how there are many different ways to query the data frame and interesting side implications that come up when doing so.